Section 4. Counting atoms. Objectives. Compare the quantities and units for atomic mass with those for molar mass. Define mole and explain why this unit is used to count atoms. 3. Calculate either mass with molar mass or number with Avogadro's number given an amount in moles. Atomic mass. You would not expect something as small as an atom to have much mass. For example, copper atoms have an average of only 1.0552 times 10 to the negative 21st kilograms. Each penny in figure 23 has an average mass of 3.13 times 10 to the negative 3rd kilograms and contains copper. How many copper atoms are there in one penny? Assuming that penny is pure copper, you can find the number of copper atoms by dividing the mass of the penny by the average mass of a single copper atom, or by using the following conversion factor. 1 atom copper divided by 1.0552 times 10 to the negative 27th kilograms. 3.13 times 10 to the negative 3rd kilograms times 1 atom copper divided by 1.0552 times 10 to the negative 25th kilograms equals 2.97 times 10 to the 22nd copper atoms. Masses of atoms are expressed in atomic mass unit. Obviously, atoms are so small that the gram is not a very convenient unit for expressing their masses. Even the picogram, 10 to the negative 22nd gram, 10 to the negative 12th grams, is not very useful. A special mass unit is used to express atomic mass. This unit has two names, the atomic mass unit, AMU, and the Dalton. In this book, atomic mass unit will be used. But how can you tell what the atomic mass of a specific atom is? When the atomic mass unit was first set up, an atomic mass number was supposed to be the same as the atom's mass and atomic mass units. Mass numbers and atomic mass units would be the same because a proton and a neutron each have a mass of about 1.0 AMU. For example, a copper 63 atom has an atomic mass of 62.940. A copper 65 atom has an atomic mass of 64.928. The slight differences from exact values will be discussed in later chapters. Another way to determine atomic mass is to check a periodic table, such as the one on the inside cover of this book. The mass shown is an average of the atomic masses of the naturally occurring isotopes. For this reason, copper is listed as 63.546 instead of 62.940 or 64.928. Introduction to the mole. Most samples of elements have great numbers of atoms. To make working with these numbers easier, chemists created a new unit called the mole. A mole is defined as the number of atoms in exactly 12 grams of carbon-12. The mole is the SI unit for the amount of a substance. Chemists use the mole as a counting unit, just as you use the dozen as a counting unit. Instead of asking for 12 eggs, you ask for 1 dozen eggs. Similarly, chemists refer to 1 mole of carbon or 2 moles of iron. To convert between moles and grams, chemists use the molar mass of a substance. The molar mass of an element is the mass in grams of 1 mole of the element. Molar mass has the unit grams per mole, G/mol. The mass in grams of 1 mole of an element numerically equal to the element's atomic mass from the periodic table in atomic mass units. For example, the atomic mass of copper to 2 decimal places is 63.55 AMU. Therefore, the molar mass of copper is 63.55 grams per mole. Skills Toolkit 1 shows how to convert between moles and mass in grams using molar mass. Scientists have also determined the number of particles present in 1 mole of a substance, called Avogadro's number. 1 mole of pure substance equals 6.0221367 times 10 to the 23rd particles. To get some idea of how large Avogadro's number is, imagine that every living person on Earth, about 4 billion people, started counting the number of atoms of 1 mole carbon. If each person counted nonstop at a rate of 1 atom per second, it would take over 3 million years to count every atom. Avogadro's number may be used to count any kind of particle, including atoms and molecules. For calculations in this book, Avogadro's number will be rounded to 6.022 times 10 to the 23rd particles per mole. Skills Toolkit 2 shows how to use Avogadro's number to convert between amounts in moles and the number of particles. You can see the Skills Toolkit here. It's determining the mass from the amount in moles, and they're doing various calculations here. I included this picture so you guys could see it. We will discuss this further later. Sample problem D, converting from amount in moles to mass. Determine the mass in grams of 3.50 mole of copper. Step 1. Gather information. Amount of copper equals 3.50 moles. Mass of copper equals grams copper. Molar mass of copper equals 63.55 grams. Step 2. Plan your work. First, make a setup that shows what is given and what is desired. 3.5 grams copper times equals grams copper. Use a conversion factor that has grams copper in the numerator and moles copper in the denominator. So here's how you do it. You can see here we've got 3.50 grams copper times whatever our grams copper divided by 1 mole copper equals grams copper. Step 3. Calculate. The correct conversion factor is the molar mass of copper, 63.55 grams per mole. Place the molar mass in the equation and calculate the answer. Use the periodic table in this book to find the mass number of elements. 3.50 moles copper times 63.55 grams copper divided by 1 mole copper equals 222 grams copper. Verify your results. To verify that the answer of 222 grams is correct, find the number of moles of 222 grams of copper. 222 grams of copper times 1 mole copper divided by 63.55 grams copper equals 3.4949 moles copper. The amount of 3.49 moles is close to the 3.50 mole, so the answer of 222 grams is reasonable. Practice. What is the mass in grams of 1 mole of uranium? 2. What is the mass in grams of 0.0050 moles of uranium? 3. Calculate the number of moles of 0.850 grams of hydrogen atoms. What is the mass in grams of 0.850 mole of hydrogen atoms? 4. Calculate the mass in grams of 2.3456 mole of lead. Calculate the number of moles of 2.3456 grams of lead. We have another diagram here showing you the skills toolkit. Determining the number of atoms from the amount in moles. In the top right box, or top left box, you see the amount. We have a question mark mole. In the top box in the middle, we have 6.022 times 10 to the 23rd atoms divided by 1 mole. And that leads us to our number of atoms, which we have a question mark for. In our bottom center box, we have 1 mole divided by 6.022 times 10 to the 23rd atoms, which will lead us back to our moles. So the point here is that they are interchangeable by using Avogadro's number. Sample problem E. Converting from amount in moles to number of atoms. Determine the number of atoms in 0.30 mole of fluorine atoms. Gather information. Amount of fluorine equals 0.30 mole. Number of atoms of fluorine, we don't know. Plan your work. To determine the number of atoms, select the conversion factor that will take you from the amount in moles to the number of atoms. Amount mole times 6.022 times 10 to the 23rd atoms divided by mole equals the number of atoms. Calculate 0.30 mole fluorine times 6.022 times 10 to the 23rd fluorine atoms divided by 1 mole fluorine equals 1.8 times 10 to the 23rd fluorine atoms. Verify your results. The answer has units that are requested in the problem. The answer is also less than 6.022 times 10 to the 23rd atoms, which makes sense because you started with less than 1 mole. Practice. 1. How many atoms are in 0.70 mole of iron? 2. How many moles of silver are represented by 2.888 times 10 to the 23rd atoms? 3. How many moles of osmium are represented by 3.5 times 10 to the 23rd atoms? Chemists and physicists agree on a standard. The atomic mass unit has been defined in a number of different ways over the years. Originally, atomic masses expressed the ratio of the mass of an atom to the mass of a hydrogen atom. Using hydrogen as a standard turned out to be inconvenient because hydrogen does not react with many elements. Early chemists determined atomic mass by comparing how much of one element reacted with another element. Because oxygen combines with almost all other elements, oxygen became the standard of comparison. The atomic mass of oxygen was defined as exactly 16. The atomic masses of the other elements were based on this standard. But this choice also led to difficulties. Oxygen exists as 3 isotopes. Physicists base their atomic masses on the assignment of 16.000 as the mass of the most common oxygen isotope. Chemists, on the other hand, decided that 16.000 should be the average mass of all oxygen isotopes, weighted according to the abundance of each isotope. So to a physicist, the atomic mass of fluorine was 19.0044, but to a chemist it was 18.9991. Finally, in 1960, a conference of chemists and physicists agreed on a scale based on an isotope of carbon. Carbon is shown in Figure 24. Used by all scientists today, this scale defines the atomic mass unit as exactly 1/12 of the mass of one carbon-12 atom. As a result, one atomic mass unit is equal to 1.6005402 times 10 to the negative 27th kilograms. The mass of an atom is indeed quite small. Section Review. Understanding key ideas. Number 1. What is atomic mass? Number 2. What is the SI unit for the amount of substance that contains as many particles as there are atoms and exactly 12 grams of carbon-12? Number 3. Which atom is used today as the standard for the atomic mass scale? Number 4. What unit is used for the molar mass? Number 5. How many particles are present in 1 mole of a pure substance?